Hi everyone, welcome back to my channel, where this week I'll be reviewing another article of interest to me as part of my continuous professional development as an engineer. In my previous video, we covered an article titled Hacking into E-Waste, looking at the global initiatives underway to tackle the problem of electronic waste from Togo to Kathmandu, whereby I included an explanation into some technical terms such as polystyrenes and polypropylenes and their uses, and how bioleaching using microbial processes can be used to extract metals such as copper. The video is in the description below. I urge you to check it out. This week I will be looking at an article featured in the November 2020 periodical titled Here Comes the Sun. It explores the materials and design challenges and solutions to get the European Space Agency's solar orbiter to achieve its objectives. Earlier this year, the European Space Agency, ESA, and NASA launched their solar orbiter following almost 3 years of project delays. The orbiter is on a mission to capture the first detailed pictures of the sun's poles and provide insights about the never-before observed magnetic environment that regulates the sun's 11-year solar cycle. It forms part of the ESA's third campaign of space exploration and science projects named Cosmic Vision, which is set to last until 2025. The solar orbiter aims to expand humanity's understanding of how the solar system works, one of the core aims of the Cosmic Vision campaign, by investigating the link between the Sun and the heliosphere. Staying in close orbit over 696,340 kilometer sphere of burning plasma is no easy feat, demanding the highest caliber of materials and design engineering expertise. Since the €300 million contract for its construction was first awarded in 2012, the solar orbiter has garnered much attention in the scientific community. In addition to the contract for construction, the project involved the development of 10 scientific instruments funded by the USA and the member states of the ESA. Of the 10 instruments, 6 are used for remote sensing, including imagers and ultra-sophisticated telescopes used to see the sun from a distance. The other 4 are fixed to the orbiter, measuring the environment surrounding the spacecraft, including the solar wind plasma and electric and magnetic fields. The orbiter will need to fly inside the orbit of Mercury to complete its mission, so it can observe solar wind before it becomes disrupted by the magnetic fields of the other planets. At its closest, the orbiter will monitor the distance at a distance of 42 million kilometers, which is just over a quarter of the distance between the star and our planet. The mission will last 7 years, and by the end of 2026, we should have close-up pictures of the 180-kilometer wide solar landscapes to explain why glowing gas forms loops in the strong magnetic field. Capturing the images is a tremendous challenge. The orbiter will be exposed to heat 13 times more intense than on Earth. At its closest approach, 42 million kilometers from the Sun, the spacecraft will need to resist eruptions and explosions of energy caused by the magnetic forces or solar flares. At this distance from the Sun, any exposed telescopes and cameras that are directly pointed towards it can overheat and become damaged. Previous missions that have flown within similar distances, such as Helios in the 1970s, avoided overheating by not containing any telescopes or imaging instruments and spinning once per second to evenly distribute heat. The engineers behind the solar orbiter decided on a unique design that not only met the weight criteria required for deployment in space, but also included effective thermal management. Hold on a second, they said spinning once per second to evenly distribute heat. Just imagine how quickly that must be. Although the ESA has not disclosed all the materials that have been used, we can make some reasonable assumptions. Much of the design has been inspired by the Eurostar 3000 spacecraft design, a model of commercial and military satellite often produced by the Airbus Defence and Space. This is typically produced using aluminium, carbon fiber, and steel. Although each of these materials provides an ideal lightweight solution due to their low densities, aluminium has a melting temperature of 660 degrees Celsius. not much greater than the temperatures of 400 degrees Celsius and above experienced within Mercury's solar orbit. To reduce the exposure to the extreme solar temperatures, the design therefore includes a specially developed heat shield, also known as the sun shield. This shield has the shape of a 3.1 by 2.4 meter sandwich with a thickness of 38 centimeters and allows the orbiter to constantly face the sun by acting as a barrier between the spacecraft and solar radiative heat. To resist temperatures up to 600 degrees Celsius, the sun shield is made from titanium, aluminum, and carbon fiber. The front layer, which is closest to the sun, consists of wafer-thin sheets of titanium foil to reflect heat. It is only 0.05 millimeters in thickness and is backed by 18 layers of a titanium multi-layer insulation. The front layer is connected using titanium brackets with a honeycomb structured aluminum panel closest to the spacecraft to provide support to the shield. This aluminum base includes further insulation and is covered in a carbon fiber skin to protect the spacecraft. Carbon fiber plays a key role here due to its high thermal conductivity and low coefficient of thermal expansion. In between the front layer and the support, a 10-inch gap funnels heat out of the shield and into space. A further gap fulfills a similar purpose between the support and the spacecraft itself. The shield is also fitted with several windows for sun-facing instruments to temporarily pass through to get a direct view of the sun. However, the titanium used on the front layer would not be suitable for use uncoated. Titanium offers high heat reflectivity, but in the process, it would significantly increase the heat shield's temperature. According to ESA thermal engineer Claudio Damasio, an uncoated titanium front layer would have led to temperatures of 700 degrees Celsius on the sun-facing side of the heat shield. Adding extra layers to the shield mitigates the impact but increases the overall payload. Instead, two coatings, solar black and solar white, were shortlisted to coat the titanium. Developed by mechanical engineering company ENBIO, in collaboration with ESA and Airbus Defence and Space, both coatings are made of calcium phosphate and applied to titanium using a technique called co-blast. This involves grit blasting away the titanium surface oxide layer to chemically bond the coating, fixing it to the substrate metal. The black calcium phosphate that makes up solar black gives it high emissivity and high solar absorbance properties, helping it mitigate extreme solar radiations. Solar white, meanwhile, is an inorganic coating that handles electrical conductivity better and can help the orbiter prevent electrostatic discharges. Both coatings can be applied to metallic substrates, including the aforementioned titanium, aluminum, copper, and steel. Solar white was set to be the coating for the solar orbiter. However, the engineering team realized that when exposed to a high volume of ultraviolet radiation, the white coating would gradually darken over the duration of the mission. This change in color would result in more wavelengths of light being absorbed, in turn affecting the shield's thermal properties. The solar black coating was found to retain the same black color across the project's lifetime, allowing the shield to maintain thermal stability for a maximum surface temperature of 520 degrees C. The materials used in the orbiter's instruments and antenna, as well as their deployment mechanisms, were also carefully considered. Although each of the instruments faced similar challenges, one of the most interesting impacted on the orbiter's antennae. The solar orbiter's primary purpose is to relay images and sensor information back to Earth. Key to this is the craft's antennae, which have to deploy fully and withstand the environmental conditions. Extending out slightly beyond the sun shield, the antennae are designed using titanium and again coated in solar black. However, the antennae's length requires it to be stowed during launch and deployed smoothly in orbit. This deployment mechanism comprises several shape memory alloys, also known as SMAs, components with each antenna designed based on multiple segments that connect the SMA hinges. When stowed, each antenna is kept in place by 3 hold down and release mechanisms, HDRMs, that when opened in sequence release the device. For each HDRM to release, shape memory alloy based frangibolt actuators and hinges activate, allowing 2 stowing flanges guided by bearings and driven to their open position by springs. As some SMAs are activated at a certain temperature, the temperatures of these components are highly regulated to avoid premature deployment, achieved using multi-layer insulation shells around the frangibolts. There are several SMAs that could perform the martensitic transformation required. Nickel titanium alloys, which are often used in satellites, boast a melting temperature of 1310 degrees C and have a transformation temperature of approximately 100 degrees C, making them well suited to activate in solar orbit. Each part of the solar orbiter demonstrates the importance of careful material selection and consideration during the design stages. If there were even one inaccuracy in the properties of the materials used in the orbiter, the project would face an expensive failure. In July, the first images were published of the spacecraft halfway between the Sun and the Earth. The images are the closest ever taken of the Sun and showed new details of the star's surface. As you can see, getting a spacecraft to image the Sun presents many challenges that have forced engineers and material scientists to become innovative with our current material science and technology to develop materials such as solar black and shape memory alloys. Many thanks for listening. Do let me know if you'd like me to cover any other topics in the description below, and I look forward to seeing you next time.